Hi, I am Parvashit, and in this video I am going to talk about charge coupled device sensors. A CCD is nothing but an electronic eye that provides vision to a machine, thus becoming the most important component for any robotic and autonomous technology. Not only for intelligent machines, but also for any purposes where high definition images are a requirement. A charge coupled device is what you rely on these days. We will begin with realizing the impact this technology has and why it is important to know more about it. We are nearing the end of 2019, and at this moment, the use of these charge-coupled devices has become so common that its existence in any device usually goes unnoticed. But this does not make its invention any less important. Today, the CCD sensors have a huge contribution in the various industries, spanning from the sectors of consumer electronics, defense, medical research, and even outer science exploration. From high-definition astronomical imaging, such as that in the Hubble telescope, that in the simple CCTV cameras being used in any office or home, CCD sensors make it all possible. It is difficult to imagine the existence of biomedical imaging fields without the existence of CCD technologies. Listing the applications of CCD, there are many. Instead, a suitable metric to demonstrate its impact on the industry will be to showcase how much market it captures. According to CAGR, the CCD market stands at 1.72 billion US dollars as of 2018 and is expected to grow up to 2.45 billion US dollars over the next 5 years. These figures itself demonstrate how big an impact this technology has on the industry and why we are motivated to learn more about it. Let us now explore the history and origins of this technology. It was at the Bell Laboratories in October 1969 that two scientists, William Boyle and George Smith, trying to save the funding of their project, came up with a unique idea in less than an hour of brainstorming. Boyle and Smith came up with the idea for the CCD, sketching out the basic design, principles of operation, and preliminary thoughts about applications during that session. The two were working on semiconductor integrated circuits, and Smith had been involved with trying to create an imaging chip for the picture phone, which consisted of an array of silicon diodes. At the time, Bell Labs was also working on a new type of computer memory that relied on tiny bubbles of magnetism. Upper management was anxious to speed up the development of magnetic bubbles as a major memory technology, and the pair was encouraged to come up with a compelling semiconductor device, or potentially risk losing funding. Little did they know that their invention would fetch them the Nobel Prize some 40 years later. Just a year later, after the ideation, they came up with the first solid-state camera device, and that is where the revolution began. This opened up the market for electronic imaging sensors, and by the mid-1980s, the market was flooded with varieties of NMOS and CMOS sensors based on a similar concept. Also, the early CCD sensors suffered from a problem of shutter lag. This was largely resolved with the invention of pinned photodiodes, which was a photodetector structure with low lag, low noise, high quantum efficiency, and low dark current. So, from 1987 onwards, PPDs were incorporated in all CCD systems. By the early 2000s, we predominantly started to switch from the primitive chemical imaging to this more advanced and higher quality electronic imaging. The early invention of this technology and periodic modifications and upgradations to it have made it extremely mature today, with the state-of-the-art achieving very high quantum efficiency and very low dark currents. To understand what these parameters mean, we need to understand the technical details of how these devices work. Let's have a look at that next. So, CCD is a device based on the phenomena of photoelectric effect. The photoelectric effect is the emission of electrons or other free carriers when light hits a material. Electrons emitted in this manner can be called photoelectrons. Here, the material chosen is a p-doped silicon wafer with a capacitor attached to it to collect the generated electrons. The wafer is divided and isolated from each other into small sections called pixels. When the wafer interacts with incident light, photoelectrons or charges are generated. These charges are accumulated using a shift register and are processed to generate information about the incident signal pixel-wise. Thus a high-quality image can be formed. The choice of silicon here is motivated by the fact that the bandgap of silicon lies in the range of visible and ultraviolet light, and thus imaging in these regions become possible. The shift register mentioned works as follows. The applied positive voltage at the gate electrodes helps create potential wells for the accumulated charges. The charges remain confined in these wells, and a sequential application of gate voltage helps transfer the accumulated charge. In real time, when light is projected on this capacitor array, an electric charge proportional to the light intensity at that location is developed. Then, a control circuit made up of these resistors causes each capacitor to transfer its contents to its neighbor. The last capacitor in the array dumps its charges onto the charge amplifier, which converts the charge into a voltage. By repeating this process, the controlling circuit converts the entire contents of the array in the semiconductor to a sequence of voltages. In a digital device, these voltages are then sampled, digitized, and usually stored in a memory for the construction of an image. Some important parameters that define the quality of these devices are the quantum efficiency, the dark current, and the power requirements for operation. Quantum efficiency is defined as the number of photoelectrons generated per photon. Hence, this is actually a measure of the sensitivity of the device. The dark current refers to the existence of charges for no light incidence. This is an extra term that does not represent the original signal and needs to be as low as possible. The power requirement is another factor that is used to compare the image sensor technologies amongst each other. It is always better to have a device that consumes less power. Since we know the basic parameters for comparing the performances of image sensors, let's look at CCD's competition and compare their advantages and disadvantages based on these factors. The major competitor for CCDs at the moment is the CMOS sensor. Unlike CCDs, which are basically metal oxide semiconductor capacitors, the CMOS image sensors are based on the MOSFET technology. As we saw in the case of CCDs, the amplifiers are present at the edge of the last capacitor layer. On the other hand, in the case of CMOS image sensor, each pixel has its own amplifier. Here, the property of using a transistor as an amplifier is used. This makes the processing faster as simultaneous amplification and processing is possible. Comparing the advantages and disadvantages of each of these devices, we can say that for CCDs, it is possible to have a very high quality and low noise with these devices as they have a very high quantum efficiency as compared to other image sensors. So, CCDs are a better option when quality is of utmost importance. Also for the case of video imaging, CCDs turn out to be handy. One more advantage of CCDs is that the output obtained through them is raw data. According to the sushi principle, raw data is more useful for data analysis and drawing deep, unintuitive insights. For example, let us consider the scenario of astronomical imaging. It is always better to obtain raw data so that further insights can be drawn, which a direct image would not reveal. Some disadvantages of a CCD sensor are, it consumes very high power as compared to CMOS image sensors, almost hundreds of times. This is because a large amount of voltage is required each time to shift the charges sequentially. This makes the overall operation of the CCD sensors costly and so limits its use to the areas where quality matters more than the costs. Another disadvantage is that due to the presence of an amplifier at the edge, the amplification and processing becomes serial and thus is more time taking. On the other hand, for CMOS, the advantages are that it requires very low power. Also, due to the presence of an amplifier at each pixel node, parallel processing is possible and the image capture can be done faster. A big disadvantage of CMOS image sensor technology is its low quantum efficiency, due to which it is less sensitive and more susceptible to noise. The quantum efficiency for these devices is low due to the presence of a large number of non-photosensitive elements present per pixel, that is, the presence of a large number of transistors surrounding a single pixel. This reduces the effective surface area for the photons to generate photoelectrons, and hence reduces the quantum efficiency of the device. So, from this we conclude that CMOS is a cheaper technology and great for applications where low to medium qualities of images are enough. Whereas for any sophisticated situation such as that of medical imaging, advanced scientific research, astronomical imaging, or even industrial process flow regulation, CCDs do not have a competition yet. The future for this technology looks bright, but could be even brighter if the issues of high power consumption and cost are addressed satisfactorily. With this, I conclude this discussion of charge coupled device sensors. Thank you for your time.